Okay, welcome everybody. Shutting the doors so we can begin. Thank you very much for being here. Lovely to see a big audience.
My title involves a new era in physics. Now, it really is in physics rather than a new era totally, because, as you just heard, I'm using ideas which are already current in biology. They're maybe not known to so many people. A lot of biologists are reductionistic and don't realize there's more going on behind. But anyway, so I'm really, some of these ideas are my own or those of our group, and but a lot of the time I'm just applying existing ideas. But the question is now, can you connect them with physics? And one specific connection that I'll talk about is group theory, which in yesterday's talk I was pointed out to be an extremely important aspect of physics. So let me go on. I think, first of all, I have acknowledgement to my colleagues. Mrityunjay is from India, and when he was just finishing his PhD, he said he'd like to discuss things. So we talked about how my work connected with what he knew about in Vedic science, Indian philosophy. And then we're joined by Scott Kelso, who I think ought to be getting a Nobel Prize at some point for his work in coordination dynamics. And Alexa Yardley, well, that's a very strange thing, a circular theory. I'll say a little bit about it in the end, but we had some discussions there. But anyway, okay, my main thesis is biology has certain structural aspects, and these are equally important in physics. In fact, there are connections between quantum physics and mind. So physics is getting it wrong. The time on theory of everything and standard model is rather being wasted. People are trying to connect standard model and gravity, but in fact, rather than a theory of everything, there are lots of different approximations. That's the true facts, and that's what we need to work from. But I'm going to start from the work of a physicist. Of course, I could mention David Bohm, but I think what Wheeler said is more relevant here, because Wheeler, he actually wrote an article called Law Without Law, and his idea is that not fixed laws, but laws that develop. And this was through the way observers participate, which is part of quantum mechanics. So he really started from quantum mechanics, and Bohr said that what observation does is to make certain things definite. You say observe a position, and then something happens to the observed system, the position becomes something definite. So Wheeler basically was saying, well, I think the laws of motion, the laws of physics, laws of nature should come out by the same process. Observers are in some way creating them. But that would require some kind of intelligence. Random observation won't do it, but it would have to be goal-directed. And he had a picture of it. I guess you can't see the details, but anyway, I'm not going into the details. But he had things going in a sequence. There may be something in that sequence, but he hasn't got the details of how you step from one position to another. Okay, I'll just mention literature references. Now, since the talk is being recorded, you don't need to write them down now. You'll get it from the recording. Just leave it there another couple of seconds for, anyway, presumably you can pause the recording. Well, I'll just say Kelso is one of our main collaborators. He has a very nice book on article on coordination dynamics, explaining it all. Preprints and other things like that. Terry Deacon has ideas about how mind emerges, how language develops, evolves. Kaufman has a book, World Beyond Physics, where he says he's really against reductionism and saying we need to look things differently. There are things like causal closure, and Barrard was a quantum physicist who took Bohr's ideas and again talked about how articulation or talking developed things. Okay, now, so I'm going to talk mainly about coordination dynamics. This was is a subject of how, as Kelso put it, coordination is found everywhere in biology, but we want to treat it theoretically. And the main point is that there are units called synergies. The synergies are functional, they do things. So that's different from what kind of thing happens in physics. You do get things coming together in an organization, but they're not functional and there isn't a hierarchy. So there's a hierarchy of these synergies. And a way of explaining how this happened, one is to say that units form but are also dissolving, and this is the result. Another way is two different opposite processes. You talk about systems going to equilibrium and systems fluctuating, but perhaps those fluctuations also organize and go to equilibrium. So these things go mysteriously together, and I think this is what these synergies are about. And biology knows about them, but physics hasn't. I don't think, well, of course, people expert in it may contradict me, but I think this is an aspect of things that complexity theorists in physics have not got into. So obviously I have very little time, so I can't go into much detail. But I'll just mention that there's a model that supports it. I'll go into that theory. So I'll just talk here about wholes and parts. Let me see if I can point here. Yes, here you have parts going together to form a whole, but then these wholes go together to make a bigger whole and so on. So that's basically what this whole part hierarchy is about, and these are what these synergies are. Now, it's genuine science, not philosophy, because people do create models on this basis and they compare them with experiment. I'll do just one example in a minute. Anyway, as I said, these synergies are functional groupings of structural elements that are temporarily constrained to act as a single coherent unit. That was from Kelso's article about it. Now, I think he says in that article, this is how living systems handle complexity. He didn't quite say, but probably had it in mind, that living systems have to do certain things in order to survive. And if they build these structures, they can help use these structures to survive. So that's basically why we get these kind of structures, because they work in useful ways, basically. I just mentioned that there's a parallel with programming, because in programming you use functional structures. You write functions, and these functions create new functions. So it's not just in biology that you get this kind of structure. But of course they're formed in a different way. These synergies appear naturally rather than being done by a programmer. Okay, you probably can't see this, but this is from the article, and he has a set of the distinction between coordination dynamics and ordinary physics, the way it uses different concepts. I don't know if you can see it now. Mm-hmm. I can certainly see it from here. Anyway, different things like fixed laws, extensible laws, and regularities on the other side. So that's the difference. Now, I said I'd give an example of it in use. It turns out that to make useful models, phase relationships are very important. And one way these enter into the adaptation process. What happens is you have a certain structure, and when the environment changes, they change. The whole structure's the same, but the phase relationships switch to a different form. And again, you can find situations that fit that picture. Now, there's this couple oscillator model with just two oscillators being coupled. That's a simple version of synergy, and you get these various graphs. So the equation at the bottom is the equation from which she's come about. There's the so-called HKB model, and these black points will be the minimum where the system settles down. And this system settling down in ways which depend on the environment is something which fits this model very well. So it's a very useful picture. Now what I want to do is something which I think people hadn't noticed, that language fits this picture very well. So I'll try and explain it. How on earth does language work? People study it but don't really explain how it works, except that there was a chap, what's his name? He produced systemic, yes, Halliday is a linguist who produced an approach to language, unlike Chomsky, who just looked at language itself. Halliday asked, what does language do? And his idea is that language is composed of a number of pieces, and each piece does a certain job. Obviously, words characterize objects of a certain type, but the grammar helps sort out the confusion. Once you know the grammar, you don't have the ambiguities. You say, this is a phrase, and this is describing that. So grammar helps you in that way. And the nice thing about it, let me say that it's, I'll say that there's this program I'll talk about based on systemic grammar, which works very well and more or less shows this is the right picture of what language does. The whole point, though, is that systemic grammar has a lot of parts which fit together in the same way as coordination dynamics. So what one finds, and which I found more and more as I prepared this talk, is that different approaches are really parts of the same field, the same concepts that have been found to be useful in different places. And here we have a case of language operating in the same way as coordination dynamics. Okay, so it has these interconnected units, and I'll explain that. But the point is that if you ask how are these connected, it turns out that you can think of it in terms of a flow chart, which you have in computer programming. And this says how, when you're in one situation, you've got certain choices. This is the point that Halliday makes, that at any given point when you're thinking of something to say, you have certain choices in how to express it, a small number of choices. This is like somebody who produced scheme theory, which also has a similar structure once again. Anyway, here's a flow chart, and you see you have hierarchies, these units, forming units, and so on. But the flow chart is the actual dynamics, how you switch from one system to another. And this is what holds the whole system together. And now, this is what a language is, but how does it develop? Well, the argument there is that there are certain practices people have which are to be useful, and these practices get implemented in the language. Like different languages, like German puts the verb at the end, which is very different from English. But that was just a practice that developed at a certain time. And this is repeated in people's minds, and that's the language. And there is something in coordination dynamics. This is, Scott let me use one of his slides. This is about how different levels connected. And this happens in, for example, the laser where you have fields and spins. The spins determine the field, and the field organizes the spins. So that's a connection known in physics. And the argument now is the same thing happens. Discursive practice affects the structure of mind, and the structure of mind affects your discourse. So that's another piece of a picture. Right, so you have this underlying system which develops, and for it to work, you do things in an order corresponding to a flow chart. So I say that we do have a definite theory of this complicated thing called language, and this is something which seems to be something very powerful. It happens, physics doesn't know about it, but that's what should happen in fundamental physics as well. So, oh yes, I mentioned this simulation, which shows that there really must be something to this theory. What Winograd did was he wrote a program based on systemic grammar. His book, or his published paper, discusses all the details. He says this structure corresponds to this, and you have these connections corresponding to a flow chart. So he made this very complicated program just based on systemic grammar. Then he had a simple computer simulation of a world of blocks. And then you could ask questions like, is there anything which is bigger than every pyramid but is not as wide as the thing that supports it? Pretty complicated sentence, but it gets the right answer just because it has this language system built in on the basis of systemic grammar, which also fits with the coordination dynamics. So we have what seems to be a real theory of how things are. But of course, we need to work on the details, but this would be the principle on which our new physics would develop. Okay, I'll go on in a minute and talk about how you can fit group theory to all this. I'll just mention circular theory. Alexa Yardley wrote to me, I think in about 2007, to discuss her ideas, and they all seem very strange. Everything's a circle. Well, the way you could put it, the way I thought I'd explain it here, is that in, say, galaxies or star clusters, you have pairs forming. That's a standard thing. Pairs form that go around each other. So her circles are somewhat similar. Pairs that go around each other. And she says this is, there's a multitude of these, and that's what reality is composed of. And there are these things in her book, Circles Make Circles, and so on. So I think there are lots of things there which we really we need to look at to see if these can fit in with physics. But here's something more familiar. Oh yes. There's this mysterious pi which links the line and the circle. This is something which actually fits with something called semiotic theory, the theory of signs. So that is built in somehow, which you don't have very much in coordination dynamics, but there's a field of biology called biosemiotics which studies it. So again, I think we have to look into what she's saying in her book. But now I'll mention another thing, that water seems to have its own language. You feed signals to water and you get patterns like this. I don't know, I don't think I'll play it now, but perhaps later on I'll play this. This is, I forget what it's called, a familiar piece of music, and you can see all the patterns changing. So another bit of this theory that code has effects, code organizes, seems to be explained by what happens with water. And so our idea is that this situation, which is familiar in biology in the context of language, that is the same thing applies in fundamental physics. And there's a background which has the same fundamental background, and the background self-organized in the same way that language occurred, and that has a mind-like ability and can then do things. As I said, we want to see how much we can connect with physics, and one thing I've done so far is yes, how groups come about. Nobody said this, your picture is wrong, so I'm assuming this is right, but it's a very simple picture of how groups can arise in this picture. Scott does talk of symmetries, but not complicated symmetries like groups. So, you put it this way, when you do something, you're following a certain trajectory in whatever space it is, a well-defined trajectory. But then that trajectory will change when the situation changes, but also when you're learning, you try something a bit different. So my claim is then there's a whole set of trajectories which you can follow with any given skill. These trajectories, for those who are familiar with abstract concepts, are points in a space. And the ability to move from one trajectory to another is something that you learn. There's something corresponding to that. So what I'm saying is that there's something corresponding to a group element. These changes you can make are things that behave like a group. And things might get extremely complicated, but you may get a kind of closure. And instead of being able to make arbitrary changes, you have a limited set of changes, so you have a closed group. So it seems to be a mechanism by which groups occur. Also, my collaborators suggesting ways in which sort of groups may evolve. The group may be part of a bigger group, or else the group can split into subgroups and so on. And in fact, evolution of the laws of physics might be explained in terms of groups. And as you heard in yesterday evening's lecture, groups play an important part in physics. So we have in principle the way this all happens. We just have to work in the details, and everyone working on particle physics should now shift to working out how this works. So I think I'm nearly at the end now. Yes, a summary. All these ideas seem to give us a very specific understanding of mind. It wasn't just the general shift which Wheeler talked about. We know exactly how it happened in terms of this kind of model. And one point I haven't made is that people tend to think of the mind depending on the brain and hence on matter, but all that's really important in this picture is non-linearity. Non-linear systems can develop in just the same way. In fact, that's what happens with the sound applied to water. So in other words, you don't need the nervous system to be involved. And so that's what this new era will be all about. So I'll stop there.
Thank you very much. Brian, you've taken us on quite a journey from Wheeler's musings on the implications of the delayed choice experiment to many different rounds.
Oh yes, Wheeler required backwards causation. You had to go backwards in time to affect the universe. You don't have that weird idea. You don't need that here.
I'd love to open this to questions. It strikes me that one of the aspects of this is that you're bringing together fields which really don't talk to each other. For instance, Halliday's observations on language theory, when he describes it, it sounds a bit like the formation of biological networks, elements coming together for causative reasons. But just getting those two groups of people to speak a common language is a huge task. They don't normally talk to each other. How do you begin these conversations? So I wondered, you've had lots of experience. For decades, you've been trying to talk to groups of people in different fields. Would you have any one piece of advice for how to start a conversation with somebody from really across the wall?
Well, I've been doing it here. I think you can explain them. And so I hope, there is one of the, in my list of papers, one of them is one actually written by my colleague Merton Joy on how it all works, but we're hoping to get a paper we'll put in for publication. So I hope there'll be interest in it. And everyone in the audience must talk to people and say, here's something new that we should be working on. So I hope we can spread it. These ideas are not that difficult. They're not, well, of course, some of them are mathematical, but the basic concepts don't require mathematics to be understood. I hope people have been able to follow most of the ideas now, so I think you can put the ideas over and bring people together. And of course there may be conferences at which they all come together.
Let's go to the microphones, please.
Hi, thanks for the talk. I wanted to ask, why can't we use thermodynamics and statistical physics to describe the kind of organization phenomena you were talking about?
Well, there's an important point here. Well, it is physics in a way, but it's reductionistic physics. So the key point is that units are forming. So it's really a branch of physics that hasn't been studied much by physicists. But you can model these things. There was the simple case of coupled oscillators. So it's just is something that physics hasn't been interested in, but it could be a part of physics. Yes, indeed.
Thank you. Please introduce yourself.
Hi, I'm Charles Kam from Stanford University. Thanks for the very interesting talk. I'm wondering if you have considered applying these theories to more constrained or specific forms of language, like classic poetry. And in many languages, it has rhymes or rhythms, repetition, that might make it easier to apply some of the concepts we know in physics to study and understand them.
Well, it's for the linguists really to apply systemic grammar to poetry, and I don't know if it's been done at all. It might have been. It's not so much physics you would apply it to. I think, but on the other hand, it could be that sounds have a certain effect. That's a point which I don't know whether this video should be played now. It's only a couple of minutes long. It shows Pachelbel's Canyon being played to water, and you can see it. So that is physics. So,
well, you just perhaps we've got some questions to come. We don't have so long. Maybe people could see that.
But have I answered the question? But, no, anyway. Yeah.
Thank you. So, hi, I am Mirko Rossini from Ulm University, and thanks a lot for the nice talk. Part of your research is dedicated to an analysis of language, and therefore I wanted to ask, what is your opinion of a different perspective on language, which is the one of large language models, like ChatGPT, the emergence of this new concept? Like, what do you think about that?
It could be that they respond to the grammar. I mean, probably they just happen by the way these artificial systems work. It probably learns the grammar, but unless you couple it with how it's being used, they wouldn't be picking up those ideas. It wouldn't be functional grammar. It would be Chomsky grammar, basically.
Please.
Hi, this is Li Zhang, now a postdoc at the Jülich Research Center in Germany. Actually, I just finished my research stay at TCM at Cambridge last month for visiting Professor McPenn. Actually, I have two questions have interesting. So one is, how did you make sure your model is more closer and closer to the real world? And the second question is, how did you balance the process speed with the data processing rate? Thank you.
Well, I think Winograd's program is a very good proof of that model, but obviously you would do it like in ordinary physics. You would try to produce models and see if they agree with what we've got, and you try and get gravity out of it. So it would be just like regular physics, really. Physics involves, in an earlier version of my slides, I talked about concepts. Concepts allow you to build models, and the models you connect with reality. So if you have a new concept, you can produce a different kind of model. As happened with, say, general relativity, where curvature of space comes in. So it will be just like ordinary physics, but you will just have a new picture and new kinds of models.
Okay, thank you so much for your answer.
Do you want to? You can. You're allowed to come back if you want to. Do you want to continue? No.
It's fine. Just make more opportunity for other people.
Okay.
Yeah, I will talk to you later. Thank you so much.
Thank you. Please.
Cool. Thanks very much for the talk. I'm Max from the Potsdam Institute, and it's maybe a broader or more personal question. In that I know that you have a keen interest in meditation in the Vedic tradition, and I wonder to what extent you found your explorations there to inform your research, and whether you found that valuable.
I wouldn't say it's informed my research as much as making my mind work better, and hence improving my research. So that's how it's helped.
When did the interest in meditation start? I suppose you got you were doing your work and got your prize in the Beatles era, so there was a lot of meditation around.
Well, there's a connection actually, because I was at Cornell, and there was some announcement. I thought the Beatles were going to be there, but the Beatles had taken a transcendental meditation, and there was going to be a talk about it. The Beatles weren't there, but I found the talk interesting, so I took a TM. But then in 1984, I visited India, and I took up Raja Yoga meditation then. I did an experimental test. I went to the hall where they meditated and compared the silence produced by that meditation with silence in TM place, and it seemed pretty good, so I thought I'd take it up.
How do you compare silence? Sorry.
You hear it in some way. you feel it. If you've meditated, you'll know about it. I felt it was better in a way, but I tended to be. I was less asleep during my meditation than any other kind, but now to some extent it's the music helping my meditation. I choose a certain piece of music which I feel is getting me into a good state. So I still do that, managed to do it this morning, and yeah.
It's very interesting. How long do you meditate? How long do you meditate for in the morning?
20 minutes usually. I also do Qigong. Now, where did I pick that up from? I feel that's helped as well.
Thank you. Please.
Hi, I'm Patricia Poetz from the Fritz Haber Institute in Berlin. And returning to large language models, this Winograd complex grammar model is really interesting. I wonder what are your thoughts on that compared as like an analytical approach, whereas large language models are maybe a numerical approach?
Well, I've sort of had that question before, and saying that it might get your Chomsky grammar, but unless you also look at how language is being used, you wouldn't get systemic functional grammar. So it's really not getting you to it. Did you say analytical approach, or?
Yeah, sort of like the comparison of treating something as a model, as like a numerical solution to a model, versus trying to analytically solve the solution. So if you could use a large language model to
I thought the large language models are not analytic in that way, I don't think, are they?
That's what I mean. I'm considering them more as the numerical model.
Yeah, well,
and
okay, if you want
then
to call
maybe
it
you could
that,
use the complex grammar as analytical and combine the two approaches to get more insight.
Well, I don't know. You'd have to ask people in it how much they'd got the structure of language out, because it's many levels, isn't it? So I don't know if it handles the hierarchic nature of language, but you'd have to ask people who research in it to find out if it discovered that.
Thank you.
Thank you.
Hello, thank you for the great talk. I'm Kay. I'm an astrophysics PhD student from University College London. I want to ask for your opinion on complexity in astronomy. So in astronomy, we have the interplay of physics on microscopic scale all the way to macroscopic scale, and we see pattern emerging. So I feel like there's a deep relation between complexity and there's a potential of using the theory relevant in the domain of astronomy. But I don't know how. So do you have any comments?
Actually, it came up in the talk yesterday. I can't remember. Is it John? Someone who mentioned it in his talk, and actually he was interested in it, and he's going to look into coordination dynamics, and it looks like it might be useful in that connection, because certainly that's a situation where you could be forming these structures, and then it would. Then the question is whether, well, partly what happens in the universe, but whether there may be a deeper level of physics, which is itself guiding the formation of all these clusters and all that. But certainly, astronomy cosmology is a situation where this could all be very relevant.
Thank you.
Please.
Hi. Yeah, my name's Alex. I'm a PhD student at Berkeley. It seems like you're proposing a synthesis of many fields like physics, biology, possibly the mind, based on some physical concepts like nonlinearity, coupled oscillators, the phase relationship between things. Much of your Nobel Prize-winning research was also based on those concepts. But when you have a hammer, everything looks like a nail. So I'm wondering if you feel like those concepts are really a true representation of reality, or are they simply tools that you are using to investigate relationships between very disparate fields?
Yes, I would say tools that we perhaps never get at the reality. We look at certain aspects of it. Yeah, I might actually mention one thing I've forgotten, that I talked of Harkin and his, actually the slaving process he calls it. I actually spent a week with him in Stuttgart many years ago. I don't know what we discussed at that time. But anyway, I think you could say that we investigate all sorts of different aspects of reality, and this is just a new aspect, but there may be more beyond it. Maybe in consciousness we get to further aspects. So it's we're not really getting at the reality, because the reality in any case is more complicated than any model you produce.
Thank you.
Hello, my name is Adrià. I'm from the University of Graz, and I have two questions, but I'll just put one to be brief. I want to understand a bit better what you meant with making the parallels with the language. And my question is, if you're, so when we are studying a language, we're given grammar as a guideline, but in fact there are many exceptions to this grammar, so to these rules. So, and usually these exceptions emerge mostly by chance or by necessity or by some kind of habit that people develop in their language over time. So I wonder if you can make some kind of parallel with the laws of physics, in the sense that we take them as, in fact, general guidelines, but then there are somehow exceptions, or there could be exceptions that, and all of this is part of the same system.
Well, the normal attitude of physics is that laws don't have exceptions. Your theory needs fixing if there are exceptions, so it's different in that respect. Whereas here you've got principles, and principles have applications rather than being rules. So it's a different situation, really. Yeah.
So, yeah, I would just... yeah, so if you take laws as an absolute, then I completely agree, but maybe we are just, if we take them just as grammar rules, like guidelines, then it's a bit different.
Well, I suppose you can simply say that these are the rules that apply in this situation, and they aren't always true. So that attitude is there as well. So it's only the theory of everything approach which doesn't allow exceptions, but but in a standard model, you say gravity is an exception; it doesn't apply. So exceptions are allowed in that sense.
Okay, thank you very much.
I'm afraid we're on the last question, so please.
Hi, my name is Tristan. I'm a postdoc at the University of Geneva. I have maybe a naive question, but so let's say I want to teach this new era and new models to kids at school. What would be the best working example that you could provide so that the ideas are transmitted?
Well, I suppose our paper when it comes out, or you could. I don't know whether
Might be a bit complex for kids at school. No?
Yes, I think even the yes, I guess even this talk is too complex. So, well, okay, you could talk about organization, and that's you could say physics isn't really talking about organization, whereas biology does. You think that would do?
So, Brian, just to conclude very briefly, you're advocating for a new approach. You're advocating for a new era. What would you like the result of this talk to be in the audience?
Well, I hope it will trigger things. Well, it's different from, I have given talks previously, but I think I hadn't got the holes. It wasn't a thing you could really use to research from, whereas I think you can base research on these ideas. So therefore, I think people will push that attitude. And I mentioned to somebody at dinner a couple of days ago, sorry if you're working on string theory, you've lost your job.
Okay, well, we started depressing, we finished depressing. Well done.
Right.